Okay, so we're going to prove here the mid-segment theorem, and let's talk about what the mid-segment theorem is. Let me put that up here. This is sometimes called what we're calling the mid-segment theorem. Oh boy, computer running slow. Let's try that again. Mid-segment theorem. So what is the mid-segment theorem? Well, it has to do with triangles. So let's start by just making some kind of triangle here. There we've used our polygon tool to construct a triangle. So the mid-segments are the segments that connect the midpoints of the two sides of the triangle. So there we have a midpoint. I use the midpoint tool for segment AB and the midpoint tool for segment AC. So then the mid-segment would be the one that connects D and E. So let's look at that here. I'm going to connect D and E, and now we have DE being the mid-segment of triangle ABC. Well, some things we can notice about it. First of all, it looks to be going in a similar direction as BC. Why don't we measure its slope? We can take the slope measurement tool and we see that they have the same slope. So what this tells me, if I look at the slope triangle, it says for every 1 unit of run, there is a half a unit of rise. Okay, so that the rise is 1/2. 1/2 unit of rise for every 1 unit of run. Or if I made 2 units of run, there would be 1 full unit of rise. And you know what? The same thing's going on here. For one unit of run, we have a half unit of rise. So we call that a slope of 1/2. Okay, would rise 1 over a run of 2, right? 1 over a run of 2. So it's basically called 1/2, okay? So they both have the same slope. So if they're rising at the same rate, when will they ever meet? When would these two ever meet? The answer is they won't. So anything that has the same slope will never meet. Unless it's the same line, then it always meets. It's the same exact line. But two different lines, but with the same slope in the same plane, are never going to meet. And that's an important thing to know. If they won't meet, we call them parallel lines. So we can say that parallel lines have the same slope. And let's see if that's always true. Well, what we do is if we drag and change our triangle a little bit, okay, we can change it. Notice that by changing this does not change the slope. The slope's always the same. What if I change C? I get the same slope there on each one of those. It appears to be that no matter how I change C, I'm going to have identical slopes here. Same thing with B. Same slopes. So this is something mathematicians figured out. Hey man, the mid-segment is parallel to the base of that triangle, right? I mean, if I consider this the base, it's the segment opposite the mid-segment, but it's parallel to it. Now, another thing that they noticed, I want you to look right here at the length of DE. So to find the length, we're going to use this distance or length tool. Let's click on DE, and you can see it says 1.84. That's going to be rounded, of course, and this length here is 3.67. Boy, they are pretty darn close, right? Let me undo that last bit right there and just move that number. So 3.67. I wonder what happens if we change. Boy, that's awful close to double. And I think because there's some rounding there, that is 2 times 2 is 4, and 36 times 2 is 72. This is exactly double, right? And sometimes it looks a little bit off because of rounding. But basically, man, this mid-segment, mathematicians notice, it is half the distance of the opposite side, right? The mid-segment's half the distance of this opposite side. So this is the mid-segment theorem. Ready? Let's go and see if we can. We can't edit that. Let's try putting in some more graphics here, some more text. So what we're saying with the mid-segment theorem, the mid-segment theorem says in a triangle that the let's see, the mid-segment of a triangle has the same slope, or we'll just say is parallel to and half the measure of the opposite side. Okay? So that's what it's basically telling me. The mid-segment of a triangle is parallel to and half the measure of another side. And we saw that was true, you know. Look, I mean, no matter how that triangle is, this value, the slope and the measure, is tied not to AB or AC, but to BC. So that's the interesting thing. The measure of DE is tied to the measure of BC, and its slope is to as well, no matter how I form that triangle, right? The only thing that will change the measure of that mid-segment, or the slope, is to change the its opposite side, right? We get different slopes, but you can see it will not matter where A is. That is so interesting, isn't it? So now we're going to do a proof to show, and we're going to prove the mid-segment theorem. And to prove it, I would have you go to your drive, and I would have you create a new document, okay, in your geometry folder, and you are going to need to do a lot of writing in this. So this is a long one. I'm going to show you a little bit about it, okay? Basically, let's see if I can insert a drawing in here real quick. So in the drawing, what we're doing is we are making a triangle. Okay, so I want the shape to be some kind of a triangle. All right, wonder if we can kind of make it out. And then, you know, what we're going to do with this triangle is we're going to put the values on it. So let's say that this point A exists over here, so this can be point A, and it's going to be at 0, 0. Okay, and this turns out it's a right triangle. I didn't mean for that to be the case, but that's what happened. Okay, so we have point A over here at 0, 0. That'll be this vertex here, and then I'll put in another triangle. See if I can put another vertex over here, and this one we're going to call B. And we will put it in the plane, and we'll say it is 2x units. Oops. It is 2x units away from A on the x-axis, but still on the x-axis at 0. Okay. So that will be where B is going to be placed. And now C, I didn't mean for Z to be placed vertically. I don't want to do this with C, with this being a right angle. Or if I use specifically that this is going to be a right angle triangle, I might only prove it only for right angle triangles. I don't want to do that. So point C, I'm going to actually make it be some units in, you know, from the x-axis. It's going to be in some units, but not necessarily x units or anything, just its own number of units. So we'll say it's point C is going to be in, I'll say it is going to be in, let's say, 2p units, and it's going to be up to r units. Okay, so this is what we're going to do is we're going to do a coordinate proof, and in a coordinate proof you can actually use letters instead of numbers, so that when you prove things, it's true for any value. It's true for any value. 2p or 2r or 2q doesn't matter. We know one side is aligned with the x-axis, but we don't know how long it is, and the others are just, you know, in whatever direction we don't know, because 2p and 2r is not a specific direction. Okay, so now if we place ABC in the plane such that A is at 0, 0, B is at 2x, 0, and C is at 2p, 2r, we can use the midpoint formula to find the midpoint of AB. So where would that point be between A and B? It's going to be somewhere in here. So the midpoint formula is given as add together the x's, divide in half, add together the y's, and divide in half. I want to show you how I put this in here so you'll know how to do that as well. What you have to do is you have to go to Insert, and you have to select Equation. And what will happen is you see that little blue box. when you're inside that blue box, this little equation editor will show up, and you'll have the ability to enter things. So like I would use my parentheses here, right? I could use this as a little fraction template, right? And I could say inside of it, let's see, I put in, x sub a, so I could type x sub a, right? And then I would put, oh, it's so small, I'm going to have to make this bigger. And then inside of that, I would put, x sub b. So I'll put this down here, go x to the right sub b. And then if I go down, I would say over 2. So this is an example. I'm going to make this bigger here so you can see what I just typed, right? This is an example of using my equation editor. Notice the editor will, after you've inserted an equation in the document, it'll you can put in a new equation by just hitting new equation, but you're not going to be able to edit regular text as an equation, only when you go inside the equation. Okay, when you know you're inside the equation because you see the blue box appear, then you can use the equation editor, and you can do things like put the square root in there. See, if I put the square root of this, I can put that in there, and I can do square powers, and there's some neat things like if I do 5 squared, I can, oh boy, let's not put it there. So if I wanted to put 5 and squared, I go 5, Shift 6 will put me into what we call this superscript. So that's Shift on my keyboard and 6. You'll see the little arrow going up, and I can just hit squared that way. And then I go to the right so that as I continue to type numbers, you can see that I'm no longer in the superscript. This is the superscript. Down here, the A is the subscript. Okay, so the equation editor is really nice. It's a nice way in your document to type things up. And the only thing I would say is that once you type this up, it's kind of a nuisance working in the equation editor. So if I were you, I would highlight what you've done, copy it, and paste it down. And then, because you're going to be filling things in over and over and over, it's just a lot easier than, starting from scratch and getting a fraction template, etc. So what you see what I've done is I've found the midpoint. I use the midpoint formula to find the midpoint of A, B. I plugged in the x value of A, the x value of B, and I add them together, it becomes 2x, and then I simplify and reducing the 2's, and it just becomes x. I add in the y value of A, the y value of B, add them together, and then it becomes 0 over 2, and then simplified is x0, so there is point D. I do that again, the same calculations for the midpoint of BC. Okay, I plug in x value of B, x value of C, and I run through and I end up with this being my value for BC. So now I called that midpoint D, and I called this midpoint E. Okay, and so now I can say that DE, which are the midpoints of the respective sides, is now DE is the mid segment of triangle ABC. So we're going to prove that it is parallel to segment AC, and that segment AC is equal, or the measure of segment AC equals 2 times the measure of DE. In other words, that DE is half the measure of AC. So we use the slope formula for this. I've given the slope formula in here in case you've forgotten it. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I've calculated the slope by plugging in those coordinates. Remember that A and C, right, had A was at 0, 0, and C was at 2p, comma 2r. So the y value is on top, the x value is on the bottom. I simplify, get rid of that, and I've got the slope of AC. And then I plug use the same slope formula to find the slope of DE, and I can see once I simplify, I end up with exactly the same slope, which proves that they're parallel. Here I've got the distance formula. I use the distance formula on AC. Just plug in those numbers, work my way down, and get to the result with AC. And then I do the same with DE, and I can conclude when I'm done that we were trying to prove that AC equals 2 times DE, and we've got the value of AC, the value of DE, and they do show that they're equal to each other. So I would have you work your way through that, and then after you've made your document like this, you can make a move note. You can talk me all the way through in your move note, and that'll serve as your evidence. It's it is a great way to do the evidence that you understand how to prove the mid-segment theorem.